All right, we are going to talk about residual plots, R squared, and standard deviation of the residuals. So we've already talked about this problem quite a bit. We have one last thing to talk about, and we did one residual in the last video. But, you know, this data set has 21 values in it, 21 observations, so that means it has 21 residuals. And it makes an entire residual plot. So we're going to talk about what a residual plot looks like and how to read it, how to interpret it. So on your calculator, we can make one pretty easily on both the Inspire and the 84. If you scroll to the bottom of the data output, so right there it says resid. Those are all the residuals. And to be honest, that doesn't really do us much good. They're all microscopic, and we don't really want to copy all those down. I guess we could do this by hand if we wanted to, but we don't have to. So go to your home screen. Now this is after you've pressed linear regression and you've run these stats, because it stores these residuals in a list. So go to your home screen, click the graph to the right of the spreadsheet. We want to click the X variable for our X-axis. That's easy to remember. No change there. And instead of the Y, I want to click on the residuals. And we have a residual plot. I believe on the 84, if you press second stat, that's the list option. And the very last list is a list of residuals. So you would go to stat plot, click plot 1, click scatter plot, and for your Y variable, you would, while you're highlighting L2 or the Y variable, you would press second list and click resid, and then you can look at a residual plot. Okay, so there's our residual plot for the Inspire. I'm going to go back to our problem. And to be honest, all you really have to do is do a rough sketch of this thing and know how to read it. So whenever I sketch this, I'm just looking at the calculator. I'm going off of a sketch I made. So this is like a sketch of a sketch. So this probably won't be super accurate, but bear with me for a moment. Yeah, I remember this looking a touch different, but remember, you just need to do a sketch, and it doesn't need to be perfect. Then we had some down here. Something like that. I think the dots are a little bit closer together to the left, and this dot here is kind of singled out a little bit more so to the right, but that's a quick sketch. So in this problem, I would say the residual plot does not have a pattern. My pen is not working. Here, just a minute. Let me pause it while I write this novel here. All right. For some reason, my pen was not working. So there it is. That probably looked weird. Struggling, and then all of a sudden, suddenly it's there. But anyways, there is no pattern in that residual plot. It looks like random scatter. So we say that means a linear model is appropriate. So let me turn this ink off and go back. So look at that scatter plot, and then look at this scatter plot. And they have some similarities to them. So there's that and that. Remember, mine is a sketch of a sketch, so that doesn't look exactly accurate. It looked better when I did it in class. But what that residual plot is it's a zoomed in picture of that scatter plot. So when you do a residual plot, you turn the best fit line sideways, perfectly horizontal, and it zooms in on the dots. So we don't expect to see any pattern. If we see a pattern, that implies the linear model is not appropriate. So down here at the bottom, random pattern implies a linear relationship. And pattern implies a linear model is not appropriate. So while you have one example up there of random, let's look at some more examples. So here's a random picture. So we hope just a random spray of dots everywhere. Whereas maybe a pattern would look something like that. Or something like that. Who knows? So in other words, if there's any kind of pattern, that's bad. We want random pattern to be able to say a linear relationship. It sounds like I'm talking backwards, but I promise you random pattern, I don't even like random pattern. I don't know why I typed that now that I'm looking at it. We just want a random spray of dots. So, because random pattern, isn't that kind of an oxymoron? I don't know. Who knows? But anyways, there's a couple of other types of patterns that could occur, and that's at the very bottom down here. So they call it fan-shaped, but that's a pattern. So once again, rule of thumb is if you see a pattern, it is not linear. But maybe it's fan-shaped. I don't know who decided this was a fan, but that's what they call this. So it's really narrow at first, and then it spreads out. So I would say that's a pattern, or vice versa. Maybe it's really wide at first, and then it progressively narrows as you read left to right. So that's a fan-shaped pattern, and yet again, any kind of pattern is a bad thing. I need to go in and edit that top phrase up there. Maybe I should change it to no pattern implies, because just random pattern, that doesn't make sense. But anyways, implies no linear relationship, or maybe just like I wrote a second ago, linear model is not appropriate. All right, almost done. We're going to wrap up these notes with standard deviation of the residuals and coefficient of determination. So first off, if I was to take every one of those residuals, remember a residual is calculated actual y minus predicted y, and the calculator does all of those for you. So if we look at the calculator, they are right there, all of those. They get a form of a standard deviation of those residuals. So if we go back to the notes, there's the formula. So they add up, well, first they square all those residuals, they add them all up, and they divide by n minus 2, because we're talking about two variables, x and y, and they square root it. And this is a good definition right here. Typical prediction error. It's a form of an average. On average, our prediction is off by that much, whatever S is. Calculator doesn't output it. Typically, on a FRQ, they would give you S. You just need to know how to talk about it, which is in a future example. R squared, the very last thing we'll look at, that is the coefficient of determination. I think of it as like a grade. How good of a job is the linear model doing? It's explaining the variation in y. So the higher R squared is, it can range anywhere from 0 to 1.0, or it could be in percent form up to 100%. When I describe it, I tend to use percent, but you can keep it in proportion, fraction form, whatever. But it's explaining how much the dots are hopping around the line, if that makes any sense. So the higher it is, the better the job the linear model is doing. The better the job that best fit line is doing at explaining each y. So it really is kind of like a grade. R itself is measuring how strong the linear relationship is, and when you square it, it becomes a percent, a grade, how good of a job it's doing. So closer to 100%, the better the grade, and I have to say you need to memorize this phrase here. It is the variation in y explained by a linear relationship with x, or as I typed it there, but what I said is the way I write it. All right, so in our problem, let me scroll down so we have space. We haven't talked about R squared, and we had an R squared of 0.4700. And if you don't remember that, it was right here. Oops, I wrote it down wrong. I'm glad I checked. It's not 0.4700. It is 0.40997, so maybe 0.4100. Maybe I couldn't read my one. Mahmoud will laugh at that. Mahmoud is making fun of my sevens. All right, so let's define that. R squared is 0.4100. So I would interpret this in context by saying 41% of the variation. I'm not going to say y, I'm going to say the actual y, the context of y, of the variation in Gessel score is explained by a linear relationship with age at first word spoken. All right, hopefully all of that makes sense. In the following videos, we'll just be working examples. So, see you in class.